Hi, my name is David Watson. I'm an assistant professor of chemistry at the University of Buffalo, State University of New York. I recently wrote a perspective article for the Journal of Physical Chemistry Letters. The article focuses on the linker-assisted attachment of quantum dots to substrate surfaces and also on the photoinduced electron transfer reactivity of such interfaces. Linker-assisted attachment involves the use of bifunctional molecules to tether quantum dots or other nanoparticles to substrate surfaces. One of the primary motivations for doing so is to study the photoinduced electron transfer reactivity of these materials. Quantum dots are potentially very interesting light harvesting materials. They exhibit size-dependent energetics. They have very high cross-sections for multi-photon absorption, and under certain conditions they may undergo multi-exciton generation. As a result of these unique properties, quantum dots may have applications in photovoltaics, photocatalysis, or in charge transfer-based sensing. A key challenge, however, is to control the placement of quantum dots on surfaces or at complex nanostructure interfaces. A few general approaches have been explored thus far. Several groups have studied in situ precipitation or synthesis of quantum dots directly on substrate surfaces. Linker-assisted attachment is an alternative approach which may enable improved control over the size and size distribution of quantum dots on surfaces, because already synthesized quantum dots are tethered to surfaces. In addition, linker-assisted attachment may enable improved control over the distance and electronic coupling between quantum dot and substrate, which are important parameters to control in terms of electron transfer reactions. One can imagine three approaches which differ in the ordering of surface attachment reactions. Metal oxide semiconductors such as TiO2 are often used as substrates. In method 1 assembly, bifunctional linkers such as the linear mercaptoalkanoic acid shown in this example are first adsorbed to the substrate surface. Quantum dots are then tethered to the terminal thiol groups or other quantum dot binding functionalities of the adsorbed linkers. Method 2 assembly involves the same surface attachment chemistry, but events proceed in the reverse order. Method 3 assembly involves a combination of linker-assisted assembly with in-situ synthesis of quantum dots. My own research group focuses on both Method 1 and Method 2 assembly. Diane Euchre and Megan Kern, two graduate students in my group, will now demonstrate Method 1 assembly of quantum dot TiO2 interfaces.
I'm Diane and this is Megan, and we have set up an example of Method 1 assembly. We first start by functionalizing a porous titanium dioxide film with a bifunctional linker, in our case, mercaptohexadecanoic acid. Now we like mercaptohexadecanoic acid because it has a carboxylic acid on one side that can bind to the titanium dioxide and a thiol on the other that will bind to the quantum dot. Okay, and this whole thing is done under reducing conditions to prevent the formation of disulfide bonds, which actually would decrease your overall surface coverage of quantum dot on the surface. So after we functionalize the film, then we're going to soak them in different solutions, or a solution of quantum dot. And what happens is that the thiol from the linker will displace the native capping groove on the quantum dot, and thus tethering the quantum dot to the titanium dioxide film. Without the initial functionalization of TiO2 with the bifunctional linker, the quantum dots will not attach.
Now Jeremy Nevins and Kathleen Coghlan will show you an example of Method 2.
Hi, I'm Jeremy and this is Kathleen. We're going to talk about Method 2 attachment of quantum dots to metal oxide films. This method varies slightly from the method that Diane and Megan just talked to you, in that there's no pre-treatment of the metal oxide film with a bifunctional linker. Instead, the bifunctional linker is the surfactant of the quantum dot. This allows for direct attachment of the quantum dot to the metal oxide film. This gives you reproducible coverages of your quantum dot onto the metal oxide films. Now, Kathleen will give an example of Method 2 attachment.
Thanks. We have synthesized a suspension of quantum dots that have the bifunctional linker as the surfactant of the quantum dots. Adjusting the concentration of these quantum dots in suspension is one way to adjust the amount of quantum dots that are loaded onto metal oxide films. Typically in our lab we use titanium dioxide for our metal oxide. So today I'm going to be taking titanium dioxide films and soaking them in different concentrations of quantum dot suspensions. Here you can see by immersing the titanium dioxide films into different concentrations of quantum dots, we are able to vary their absorption on the film from high to low.
Fundamental studies of electron transfer reactions at quantum dot substrate interfaces have proceeded in parallel with materials assembly research. The most commonly studied example has involved electron injection into metal oxide semiconductors. Excitation of the quantum dot is followed by electron transfer into a wide bandgap semiconductor. Electron transfer at quantum dot substrate interfaces is complicated by energetic and structural heterogeneities associated with distributions of particle size, surface functionalization, and the local interfacial environment. Linker-assisted assembly is an attractive synthetic method because it probably offers maximal control over particle size and interfacial environment. Several groups have recently reported spectroscopic studies of photoinduced charge transfer at quantum dot substrate interfaces prepared by linker-assisted assembly. My research group uses steady-state and time-resolved spectroscopy to characterize such processes. Here, Casey Mulhern demonstrates the use of our nanosecond pulse laser. The laser pulse excites the excitonic or bandgap transition of quantum dots, and electron transfer processes are monitored by measuring transient absorbances and time-resolved emission signals. We recently reported that the quantum yield of electron injection from cadmium sulfide quantum dots to TiO2 nanoparticles decreased with increasing length of mercaptoalkanoic acid linkers. In this scheme, the numbers in bold correspond to the number of methylene groups in the linkers. The extent of emission quenching increased with decreasing linker length. Control experiments revealed that the emission quenching was caused by electron transfer. In addition, the amplitude and lifetime of transient bleach associated with a charge-separated state also increased with decreasing interparticle separation. Our results have shown that excited state deactivation and electron transfer at interfaces can be controlled by varying the structure of molecular linkers. Other groups, particularly Prashant Kamat's, have shown that the dynamics of interfacial electron transfer between quantum dots and substrate surfaces can vary significantly with driving force. Thus, linker-assisted assembly appears to be a useful strategy for putting together materials for very fundamental studies of electron transfer at interfaces. Certainly, many areas are ripe for exploration. For instance, a very important goal is to put together interfaces that promote rapid transfer or extraction of photogenerated electrons or holes. Also, the influence of solvation, the surface loading and packing of quantum dots, the nature of surface attachment interactions really haven't been explored thus far in terms of their influence on electron transfer reactivity. These fundamental studies, I think, are interesting in their own right, and they may also lead to the optimization of electron transfer processes for applications in photovoltaics or photocatalysis or charge transfer-based sensing. Finally, I'd like to thank the National Science Foundation and the ACS Petroleum Research Fund for supporting my group's research in this area. I'd like to thank you for watching the video, and I hope that you find the article to be of interest.